Good morning, everyone. I hope you had a pleasant weekend. Again, now everybody's saying we need some rain, and that's probably true. We get a little bit of mist and then the dry or whatever, but um, I'm still saying I think in my head, I'm telling myself that the pollen's not so bad. Um, uh, hopefully the precipitation will come in a way that is pleasant for us and not in the form of a monsoon. I know we get so much rain at times that we just reminded about times when we get flooding, and we certainly don't want that. But I hope again everybody's doing well. Uh, Last week we saw how we introduced some new analysis to the uh, study of infinite series, and that was basically through a power function. That is, the Taylor polynomial is by definition a finite power series. And so we saw that we could actually express a particular function in terms of a polynomial. And then we had a nice remainder term. I don't know how nice it was, but we saw how we could actually analyze the remainder term to see how good the polynomial was as a replacement. Again, let me repeat that, as a replacement for the function. So in analyzing the remainder, sometimes we were lucky to have a nice upper bound for the n plus first derivative. Other times you would have to actually analyze it and look for a pattern to get a nice upper bound, working with fractions, making the numerator as large as possible, the denominator as small as possible on a given interval. So a lot of just basic techniques. So we didn't find it to be as straightforward, but still something that we could do. So I mentioned at the time that would it make sense to extend these polynomials in an infinite fashion? And that's what we're going to talk about today. That is, not specifically as converging to a specific function, but how we actually treat a power series when the number of terms has become infinite. So we're going to learn a lot of nice techniques today that I think will be even more straightforward than the Taylor polynomial to give you some basically arithmetic strategies to analyze a power series. And then we want to work to how we can actually generate a power series. Once we learn how to operate with them, we'll talk about generating a power series. And then now again, we have the actual function to which the series converges, keeping our fingers crossed. That is, how will we know if we get that particular type of convergence? We'll continue to study things. So at least for now, I'm not going to let the cat out of the bag. The Taylor polynomial will have a big role in what ensues with this. So everything's going to come together and be full circle. So hopefully that'll make you feel like Calculus 1 when you finally learned the fundamental theorem of calculus and thought, oh, actually there's hope for us now that all of these ideas are tied together. So let me go ahead and share my screen. So when we think about a power series, you know, when we're doing the series, sometimes we call the generating nth term a sub n, sometimes we call it u sub n, just depending on the context, because we want to make sure everything's clear. But we'll start out with a power series looking something like this. Eventually, we will actually show that the power series, hopefully, can be illustrated to actually converge to a specific function. So for right now, we're just going to give it a generic name, just f of x. And so we'll write the polynomials that we dealt with in the previous lecture in an infinite fashion. So we'll have n equals 0 to infinity. Now, of course, we're not going to look at 0 to the 0 as indeterminate. We're just going to be flexible and say that that will be defined as 1, because lots of times with the power series, it's convenient to have n equals 0 as the first index. So when we have a 0 to the 0, we're not going to think, oh, we've got to do L'Hopital's rule and take logarithms. We're going to just relax the notation and say that that counts as the constant term. So be aware of that. So we'll have an nth term, just like we're dealing with a real series, and then the actual power, the power function. So we knew with the Taylor polynomial that these particular coefficients here, these nth terms, they had a specific form that was tied to the derivative of the particular function that we were working with. And so we needed lots of derivatives. Okay, so if we're thinking, if we're going to move this theory forward, then it's probably going to be the case that the functions have to be good functions. That is, we can take derivatives. If their behavior is not good enough for that, then we'll have to say pass for now. So usually in calculus, the only issue we have might be an infinite discontinuity, but as long as we stay away from that, we usually get a nice smooth function that has plenty of derivatives. So again, to use the calculus, at least for this type of strategy, we need functions that possess derivatives. So when we actually write out a few terms, we'll have the 0 term, again, which will be a sub 0. Again, when we think about this, just remember that we're going to be very flexible with the first term, the a sub 0. And then, of course, when n is equal to 1, we have a sub 1, x to the 1, and just continuing. So we know what these coefficients look like for the Taylor polynomial, and we're going to see that for convergent series, they actually turn out to be the same, which is very comforting, because then we'd have two different types of convergent power series, and we think, which one do we use? Well, we won't have to make that decision. So this just will go on ad infinitum. So when we think about a power series, we think about a function of this form. And then, of course, this is kind of specific in the sense that we have an expansion point of 0, but we can also think of, and I'll just use another letter here, say h of x. We can also think of a power function as being generated about c when c is non-zero. So we think of this as like Maclaurin type, and then we can think of a Taylor type. So we could have an a sub n, and then we could have an x minus c, where c is not necessarily 0 like it is up here. And of course, we can write the same type of expansion. So again, we want to be as general as we can be, but often many of our properties will be stated in this form just for simplicity. It's not that we're discriminating against the C. I think it just turns out that we get a little bit lazy. So let's say a sub 3, etc. So power series are basically infinite polynomials. And when you take more and more algebra, if you go to the university and take a more abstract algebra course, you will consider formal power series like this. So they play a role in analysis, but also in number theory, discrete math, combinatorics as generating functions and probability. So there's a wide use of these objects. Now, when we think about a particular power series, we now are steeped in thinking about, okay, if we deal with real series, we're thinking, okay, we either test it, we test it and we say it converges or it diverges. We even have tests that help us with absolute convergence, like the ratio test. And so what we're going to do is we're going to capitalize on the ratio test. So for instance, let's just look at this and see what we would get. Say we take this generic power series right here. So we have the generic power series. And I'll just say that PS for power series. And sorry, that C looks more like an O. And say And I'll just go ahead and write it again. H of x, n equals 0 to infinity, a sub n, x minus c to the nth power. And let's just say that we're interested in looking at this as a function. And so now, instead of having a completely real series, we have this variable that's placed into the generating term. And then we're thinking about, okay, well, if we put in the x, can we still apply the test for absolute convergence, that is the ratio test, and determine, for the case of convergence, the values of x that would actually give us convergence? For instance, now we're thinking of a variable function, but we still have that ratio test that says, okay, if this ratio in absolute value is less than 1, then we're going to get a convergent real series. So let's take that idea and apply it to the variable generating function or generating sequence, and then say what values of x will give us convergence. So what we can do is just be lazy, apply ratio test. I'm going to try to stick to the ratio test and not be abstract to keep everything nice and comfortable. So apply ratio test. So we'd say the limit as n passes to infinity and just throw everything in. We'll say a sub n plus 1, x minus c to the n plus 1. And now, of course, since we don't have a whole lot of stuff hanging around, we can just divide by the subsequent term or the term before the n plus 1, a sub n, x minus c to the n. So now, of course, this just looks like what we've been doing. Now we have the x that's hanging out. But now what we see here, we have the limit a sub n plus 1 divided by a sub n. And now, of course, all of the x minus c's absorb except for one of them in this particular case. Now, of course, we could have a situation where we might have a 2n and then get a quadratic. So again, we want to make sure that we always respect whatever power this may be. In this case, we're just treating it as a general n. So we have x minus c to the first power. So now, of course, if we look at this, we're thinking, okay, so we have absolute values. We can break it up into pieces. So we have the limit as n passes to infinity. So we have the absolute value of a sub n plus 1 divided by a sub n times the absolute value of x minus c. All right. So when we look at this, this is kind of a general setup here that we're going to do several times today. We see here that this particular piece of our expression, this particular factor depends on n, but of course the x minus c does not. So we can factor it. So we get the absolute value of x minus c times the limit as n passes to infinity of a sub n plus 1 divided by a sub n. It's interesting, I was going to introduce this one way, but as I start talking, I figure out another way to do it. That's the beauty of mathematics, and it's kind of like why my colleagues in English love teaching English. Because you read a work of literature and then you come up with another interpretation. So it's always evolving. So I guess even if you're not in STEM, even though we're biased and we think STEM is the end all major, everything can be really nifty if you take the opportunity to spend time on it, even the non-STEM majors. So when we look at this, we say, okay, from the ratio test for convergence, this would have to be, this expression here would have to be less than 1. So we would say for convergence, we have x minus c in absolute value, the limit as n passes to infinity of a sub n plus 1 divided by a sub n must be strictly less than 1. So now when we look at this, again, if we make the assumption that this actually exists as a real number, we can basically divide by it. So we're going to say that this exists as a real number. Now, of course, we'll think about other things, but for now, this would say, okay, well, x minus c in absolute value would be less than, and then we just basically reciprocate this. We have the limit as n passes to infinity of a sub n divided by a sub n plus 1, like that. So we basically just say we just divide by this number, and then, of course, when the limit of a quotient is the quotient of limits, so to speak. So we just flip this thing around and not have to have 1 over this. We do it in a more user-friendly way. So now when we look at this, we're thinking, oh, okay, here's an equation that we had back in college algebra. This is a conjunction. We have the absolute value of x minus c is less than r, or I'm going to call it r for now, but less than some number. Okay, well, when we look at this, we're thinking, as a real number, I guess, since we divided, we're assuming it's non-zero. And if it did turn out to be 0, we'd have to kind of look at that as a special case. But now we can see that we've got this positive number here because we actually did this. And then we've got the conjunction. So we have the absolute value that we remove and put the additive inverse on the other side and leave the actual unchanged number to the right. So let's just give this a special name for now. We're going to call this R for radius of convergence. Radius of convergence. So basically, we have a little formula for it. You don't even have to memorize it. You could say, if you wanted to compute it, you could always look at this particular construct. But now this would just simply say that x minus c lives between R and the additive inverse of R, okay? And then if we add c, we get c plus R and c minus R. So we look at this and say, okay, well, if this turned out to be a finite number, then we're thinking, all right, well, x, if it lived between c plus R and c minus R, the ratio test would say convergence for these values of x. So we're seeing this ratio test is turning out to be quite a useful tool. And then we might say, okay, this gives us a nice symmetric interval. That's what's nice about the ratio test. With the absolute convergence, it gives us this very elegant symmetric interval about C. We're stuck with it. Okay, but yay, we'll take it. So then we think to ourselves, we've got this nice open interval here, but the ratio test is not going to say anything except if you go outside of this interval, way out, then you clearly have divergence. But what would happen at the endpoints? You might say, okay, well, the endpoint is kind of a special number. And it's not kind of in the no man's land, but it's not in the open interval either. So we think, okay, we would have to test the endpoints. So when we would use the ratio test to look for an interval of x values for which the actual power series converged, we would have this and check endpoints. Now, when we check endpoints, that means we take these specific values of x and substitute them into the power series here. And then that gives us a real series. And then we're back to the previous tests. We have a series of real numbers and we can say, oh, that's a convergent P series, boom. Or no, we compare that to the harmonic series, that diverges. So basically with the ratio test, we get a set of real numbers, if we're fortunate, for which the series converges. And of course, this is absolute convergence. And then we say, all right, check the endpoints, and we may possibly add this one, both, or neither. So when we think about this could imply the following sets. We could have where we just struck out both times. We checked both endpoints and got divergence. Well, we could find a particular situation where the left endpoint worked, but the right endpoint didn't. Or maybe the left endpoint doesn't work, but the right endpoint does. And of course, we include it. And then, of course, the very best case would be C minus R to C plus R. And so as we continue to work with power series, we're always going to look for intervals of convergence that will have this shape. And then, of course, the very, very best situation would be that we would dispose of all of this and we would just get convergence for all real numbers, which would be the best possible case. And then we wouldn't have to worry with all of this. And you're thinking, when would that be the case? Well, if it turned out that this limit were actually zero, then zero was always less than one, and we have an infinite radius of convergence. So, good for us. So, and of course, what's the very worst case? The worst case would be that this would never be true. And then, of course, we'd only have convergence at x equals c, where basically the power series zeroed out to one term, the constant term. And of course, that's not very interesting. I mean, let's face it, ladies and gentlemen, the reason our calculators work is because we have convergent power series where we can actually get great decimal approximations of transcendental functions. And that's basically, if you read in the book, and this is very interesting, they'll say, well, back in the 16th, 17th century, mathematicians used these polynomials to compute decimal approximations of the transcendental functions, logarithms, et cetera. And then they make the point, well, this is highly used today. This is clearly not outdated because your calculators use the same software to do what they did by hand many years ago. So the calculus is here to stay. The calculus is why we have functioning calculators, okay? Calculators work based upon software coding, that when you input something and you press a button, that basically activates a certain level of code in your calculator or your computer algebra system, and boom, there you have it. So the beauty of the calculus is, like I keep saying, once we're forgotten about, we made our mark on the world, then those that follow us will continue to do this. I don't really see that this will ever be replaced, even though there are some skeptics out there and say, oh, well, they're limits. Well, I guess if you push anything to its extremes, you're going to have some limiting cases. But this is basically what's going on. So let's kind of put this to work and see that now the ratio test has already given us a strategy. All we had to do was just basically uncover it. And I think you'll find this to be very user-friendly. I think in a lot of cases, when students see power series and intervals of convergence, they breathe a little sigh of relief because now they see that everything that came before is utilized. And so you get additional practice with these strategies. So let's start off with a simple example. So say we have a power series. We're not really saying that it basically converges to any function. We just want to understand it in terms of an interval of convergence. So we'll start out with something very simple. So we've got a power series here. Notice we have 4x raised to the nth power divided by n squared. So basically we've got this variable, but if you like, you could also rewrite it. Nothing sacred about how it's written. So if we have n equals 1 to infinity, we could just write this as 4 to the n, x to the n divided by n squared. So now we can see that we have the coefficient a sub n, which is 4 to the n divided by n squared. And then, of course, the power function is just the x to the n. So we see that we have a c equals 0 in this case. So what we would want to do is just say, okay, what's the interval of convergence? Compute interval of convergence. Now, of course, every time you compute the interval of convergence, you automatically get the radius of convergence that you see from the absolute value equation. So again, this is all tied together, and it's probably best to just kind of jump into it, apply the ratio test, and work with it. We see we do have an actual formula for the radius of convergence here. Okay, that's an actual formula that you can use. But I found that in some cases, students get a little ahead of themselves, and it's probably better just to go ahead and apply the ratio test directly. So now we can say the limit as n passes to infinity. Okay, we'll have the n plus first term. So we have 4 to the n plus 1, x to the n plus 1, divided by n plus 1 quantity squared. Same old song and dance, at least this is repetitive. And now, of course, we can divide by this expression just by inverting and multiplying. So we'll have n squared, we'll have 4 to the n and x to the n, absolute value. Now, of course, we just play the absorbing game. So now if you see, we've got what? 4 times 4 to the n divided by 4 to the n. So we can just kind of run through them and check them off. So these are taken care of. And then we have what? The n squared over n plus 1 squared. And then, of course, we have x to the n times x, and then x to the n. Now, of course, you don't have to write out all of this algebra. You can see, well, this absorbs, I'm good with this. I just want you to feel comfortable with the algebra. Many times students will skip the majority of the algebra and make a mistake and then never find it by making an assumption that turns out to just be a careless mistake. So write this out and check it just like you've done before. So now we have the limit as n passes to infinity. And of course, the 4 to the n's absorbed, so we're left with a 4. And then, of course, here we just have what? N divided by n plus 1 quantity squared. And then, of course, the only thing that's left here is the x. So now we can just apply the absolute value to the whole thing. This will give us the absolute value of x, which we can factor. And then, of course, these two terms here are positive. So this will give us the absolute value of x, again, which we can factor. Oh, and make sure that I put the limit right beside it. Limit as n passes to infinity. And then, of course, we're left. And of course, if you want, you can go ahead and factor the 4 too. No need to leave it inside. And this just leaves, n divided by n plus 1 squared. So notice here, this just gives us 4 times the absolute value of x times n plus 1 quantity squared. So I leave the n divided by n plus 1 squared here. And these two terms have no n dependent, so we just factor them. So that's the scheme there, which I think you can see. And so now you can just run the limiting process inside. So we have 4 times the absolute value of x, the limit as n passes to infinity of n divided by n plus 1 quantity squared by continuity. Okay, and what would we do with limits without continuity? And then, of course, this limit is 1, ratio of leading coefficients. So we get 4 times the absolute value of x. Now for convergence, now some students just say less than 1 for convergence. At least for now, the ratio test would mean that we would have 4 times the absolute value of x minus 1 less than 1. So equivalently, this says the absolute value of x is less than 1/4. So now, of course, if you had just done the a sub n divided by a sub n plus 1, this would have given you r of 1/4. So now we can just see that based on the discussion we had first, this is just the r, or radius of convergence. Maybe a problem just asked for radius of convergence. I mean, I don't really think it's so important. Without the radius of convergence is good theoretically, obviously, but if you're working with a power series, you really do need to know where it converges. So this just is en route to finding the interval of convergence. But now, of course, this is a conjunction. Don't mess up the conjunctions. You should know how to prove the conjunction result from college algebra. Unfortunately, students just pretty much memorized it and never really understood absolute value. I think that's why most students struggle with absolute value, because they've never done a single proof using it. And we use absolute value all the time. So now this just basically says that x lives between 1/4, or excuse me, negative 1/4 and positive 1/4. So this is an open interval here. Again, with the ratio test, if we go outside of this, that is, we go beyond the endpoints, we clearly get divergence. However, inside convergence, but endpoints, not so much. We have to check those. So let's look at it. So let's check x equals negative 1/4. So basically what we do is we just go to the series here. We just go up to the series and replace x with negative 1/4. So we can do it right here if you like. So this will be n equals 1 to infinity, 4 to the n, and then of course we'll have negative 1/4 to the n divided by n squared. Now let's go ahead and do the algebra here. So of course we're going to get n equals 1 to infinity. And now we'll have a 4 to the n times, well, upstairs we get a negative 1 to the n, and downstairs we get a 4 to the n, downstairs in the numerator, and then of course n squared. And now of course the 4 to the n's absorb in the numerator. So this gives us n equals 1 to infinity, negative 1 to the n over n squared. But now, of course, this is something we know about from our study of alternating series. This now is an alternating series, and we see that this is a good convergence case, because now if we look at this particular case, we see a sub n is 1 over n squared, the part that's not alternating. And this clearly gives us the limit as n passes to infinity of 1 over n squared. So I think this is going to take care of both of the cases. 1 over n squared is clearly 0. And then, of course, we don't even need calculus here because this is so simple. We'll have what n is less than or equal to n plus 1 if we square them out. And then they're easily reciprocated. So we have 1 over n plus 1 quantity squared is less than 1 over n squared. So this, of course, is a sub n, and this is a sub n plus 1. So this sequence is clearly non-increasing. So non-increasing. So these are things that we already know how to do. So we get to use what we know, which is always comforting. So this implies this particular series here, right here, n equals 1 to infinity, negative 1 to the n over n squared, converges by alternating series test. So of course, this is going to imply that we include the negative 4. So at least for now, we'll just say include negative 1/4. So again, the idea here is that we're not really done until we check the endpoints, because the theory doesn't give us a specific dictate about what happens at endpoints. There's no way that it could. So that's something we have to check, and not a big deal, right? Now, of course, we can look at x equals 1/4. But now you can see that in this case, we just have the 1/4 here without the negative. So we basically get this series without the alternating sign. So we have what? N equals 1 to infinity. So we can go right back up here and use this since it's easier to work with, or I guess the first one would have been just as easy. So we have 4 to the n, 1/4 to the n squared. Now again, this will give us the series n equals 1 to infinity, 4 to the n times 1/4 to the n divided by n squared. And of course, the 4 to the n's absorb, and this leaves us with a series that we know very well, n equals 1 to infinity of 1/n squared. Now this is, of course, we know very well from the integral test. This is a convergent P series, so P equals 2. This is convergent. So when it's like this, we don't have any work to do. That's a direct result of the integral test. So again, we include 1/4. So this implies, and we can just say interval of convergence is, so we get to include the endpoint. So we'll say negative 1/4 with brackets. So again, what's important, and of course we would like it if all of our power series just converged everywhere, but that's asking too much. So when we start to generate a list of famous or useful power series, we'll go ahead and figure out what the interval of convergence is and list that in the table and have it as a reference, just like an integral table. So having a list of derivatives or having a list of integrals, having a list of like famous limits, like we have interesting limits that I gave you that list of 6 that turn out to be very useful. We can do the same for convergent power series, because again, if we're working with analysis, we'll find that maybe we use these power series lots in our computations. If you take a differential equations course, you learn how to solve variable linear differential equations using power series. And so again, we don't always want to have to start from scratch, and we don't want to have to think of everything as being built from the ground, so to speak. We want to use it and move to the next step of the problem. So now we can see that the concept of a power series at least has a theory that's manageable. So let's look at some other examples. What's interesting here, and what we'll find in some cases, is that when it comes to working with power series, we really don't know until, everything is pretty much done. We're thinking, we can look at the power series and say, yeah, that'll probably converge for some X, but it's not always the best idea just to make that assumption. Work through the mechanics of it and then say, okay, this is what I thought, but you have the verification. So here's an example. So we have the series n equals 0 to infinity. We have negative 1 to the n factorial. Then we have x minus 5. So this particular series is centered at 5 instead of 0. And then we have divided by 3 to the n. Now we know when we look at this, we're thinking, that 3 to the n grows pretty fast. It's exponential, and so does that n factorial. So there's a tug of war going on here. And so let's just look to see what the ratio test says about this particular setup here. And of course, we'll use everything that we have. We find the ratio test tends to be fairly user-friendly. So there might be occasions when we have to work a little bit harder, and I'll apprise you of that. So compute, if it exists, the interval of convergence. So now let's apply the ratio test. So we'll have n equals 0 to infinity. So we'll do the n plus 1 term. So we have -1 to the n plus 1. Replace all the n's with n plus 1 factorial. And then, of course, x minus 5 to the n plus 1. Divided by 3 to the n plus 1. Just a lot of stuff here. That's all. Just a lot of bookkeeping. And then, of course, we can invert. So when we invert, we get 3 to the n upstairs, and downstairs we get -1 to the n factorial, x minus 5 to the n. And of course, you're thinking, can we do other operations with these power series? Yes, we can formally differentiate and integrate, and I'll talk about that. So when we look at this, we're thinking, okay, there's more stuff, but it's manageable. So let's see. So we get equals the limit as n passes to infinity. So let's just go ahead and pair everything up. So we get -1 to the n times the -1, and just pair it here with the -1 to the n. Of course, those will absorb. So just check them off as you do them. And then, of course, we have the n plus 1 factorial and the n factorial. And then we've got the powers of 3 exponential. So we have 3 to the n, 3 times 3 to the n, laws of exponents. And then, of course, with the powers here, that's the easiest thing. All will absorb except for 1 power of the x minus 5. So this just, I'll go ahead and write it out, but you know, you could collapse that if you want. So let me do it. Let me do it like I've done the others. Just go ahead and write it out with the 2 factors. So now when you look at this, pretty much everything absorbs, absorb. And then, of course, I could have done the same thing here. Let me just go back and rewrite that. No need to jump ship. Just write that as n plus 1 times n factorial by definition. So I can use the same technique with all of them. So absorb, absorb. All of these are gone. Most of the stuff is gone, of course. That's what we expect. So we have the limit as n passes to infinity. You can work this many different ways and put fewer steps or less steps, but I find that if I try to minimize the number of steps, students can often miss something that's important. So if you look at my lecture notes on Blackboard, I have you compute the radius of convergence first and then go directly to the inequality with the absolute value. But I found that if powers change, students get less attentive and miss things. So I want to start this way by just appealing to the ratio test here directly so that you don't miss any of the ideas. So notice we have a -1 here. And here we're left with an n plus 1 as we just move to the factors. Then we have a 1/3. And then, of course, we just have the x minus 5. These are the surviving terms, so to speak. So now we apply the absolute value. We have limit as n passes to infinity. So of course, the absolute value of -1 is 1. And we just get n plus 1. Of course, you don't have to write the 1 clearly, 1/3. And then the absolute value of x minus 5. Now, of course, the x minus 5 and the 1/3 clearly independent of n, so they can be factored. So we have 1/3 absolute value of x minus 5. So it looks like we're in this class, we certainly do a whole lot of calculus 1. I mean, we are stuck with calculus 1. But now you can see that we're kind of stuck here. This, of course, has no impact, but this diverges to infinity. as n passes to infinity, so does n plus 1. So we just get infinity here. So this is kind of the maybe the worst case. This, of course, is never less than 1. So in this particular case, this implies that the radius of convergence, which is basically the reciprocal of infinity, which is 0. So that's a way you can uh, look at the theory here and say, if this limit becomes infinity, then that kind of, we lose hope for any interval of convergence. So now we can see that the only number for which this would have any hope would just be x equals 5. And then of course that just narrows this down to one term. So we'll just say convergence for the singleton, x equals 5. Not very interesting. So now this is what I was talking about before. If we do that, we have n equals 0 to infinity. So we have -1 to the n factorial. And so we just basically have 5 minus 5 to the n over 3 to the n. And this is what I was talking about. When n equals 0, we just basically have 0 to the 0. We don't treat that as indeterminate. We just treat that as 1 for convenience. So now when we look at this, what is this actually going to be? Well, when n equals 0, let's just write this down. N equals 0, we get what? -1 to the 0. We get 0 factorial, which by definition is 1. Then, of course, we get 0 to the 0, but we're going to define this as 1 for the series, even though that's indeterminate. We're going to relax that. I've mentioned this before. And then we just have 3 to the 0. So basically, this is all 1. We just get 1. And then after that, we just get the series n equals 1 to infinity. But now, of course, when we look at all of this, this annihilates everything. So we treat this separately, but then after this, everything is well defined in the sense of powers, and this just annihilates everything. So we just get 0. So basically, if we look at this formally, this is just 1. This term is 1, so we get 1 plus 0, which is 1. So not very interesting. So again, don't look at this as indeterminate. Just say, okay, well, we're kind of out of luck here. So when we replace x with 5 here, what does that give us? Well, in all the cases, this annihilates this term, but we have to look at the case n equals 0 separately and then define this form that's normally indeterminate as just 1, just as relaxing the notation a little bit to get that constant term. And then, of course, after that, everything's perfectly well defined. We have 0 to the 1, 0 to the 2, 0 to the 3. Those are all 0. So that annihilates this term. So we're just adding up a bunch of zeros. So, of course, when you look at this, you're thinking, why do we even bother to do this? Well, when you're analyzing infinite series and you're doing power series solutions, you can't forget the initial values of the index. You can't just assume they're 0, because if you do, you've got a problem. Okay, you just wish something to 0 that's non-zero. So this is what I was talking about before. And even though this is kind of a subtlety, it's very important. When you think about mathematics, we introduce certain conventions to make our work doable. So we define 0 factorial to be 1. 3 to the 0 is 1 by definition, and then we relax it here. So just keep this in mind as you work with power series, and don't just kind of erase it like, oh, it's no big deal. Of course, once n equals 1 and the power of 0 here is a positive integer, you clearly get 0. So that's fine. That's no question. So here's our first situation of a power series that doesn't go anywhere, no convergence except for one number, which is not very interesting, right? So again, we don't want to put it in the bad category, but it's certainly not going to help us do any interesting problems. We'll just have to look at it and say, well, we're done with that example. Now, I want to look at a situation where we have an interesting situation, at least arithmetically. Let's see here. Where's another good example? Oh yeah, here's an induction example. I think this will be interesting, and I may come back and do another problem that I'm leaving out. So here's another example. I was working on a problem with some of your classmates where we applied the alternating series test when we could have applied the ratio test. But what we found is that both setups worked. We got conclusions in each case. It just turned out that the ratio test was easier. The alternating series test required that we be a little bit more clever, but doable. So this is an example where when we start looking at endpoints, we have to be a little bit more clever because the generating term, the nth term, is written as a finite product. Now, we're going to have some formulas that we will use, but they're not going to be many in number. And so when we have a generating term or an nth term that's written as a pattern, then we have to respect that. Okay, so upstairs we have 2, 4, 6. So we're just moving along with the even natural numbers, ascending to 2 times n. And then downstairs, we've got odd factors ascending to 2n plus 1. So often what we see with infinite series is that instead of actually trying to find some type of closed form uh, uh, expression for this finite product, we just list it with the ellipsis where it's clear to the reader what is intended. And then, of course, we have x to the 2n plus 1. So now, again, we want to compute the interval of convergence. Sometimes you have to use induction arguments. You have to use something that puts everything on a firm playing field. I mean, you can't just say, well, it looks like it does this. We know that's no longer any good, especially with series. Well, it looks like it should converge. You know, I bet it converges. Well, when you're looking at the problem initially, there's absolutely nothing wrong with that. But then you have to supply the details. So now when we look at this, we go right to the ratio test. So again, replace all the n's with n plus 1. So we get 2, 4, 6. Then we have 2n, and then of course, that will leave us with a 2n plus 2. When n becomes n plus 1, that gives us 2n plus 2. And then downstairs, similarly, we have 3 times 5 times 7, ascend to 2n plus 1. And then, of course, n becomes n plus 1. That'll give us a 2n plus 3. So the next odd factor here is 2n plus 3. So that's clear and that makes sense. And now up here we do the same thing. We have x, replace n with n plus 1. So that gives us 2n plus 3. So when you do these problems, you do have to be careful with the powers. And this is why I tend to focus more on the ratio test here, just so that this doesn't slip. If you get a little bit too quick in your execution, then you miss some really important details. And now what we can do, now here's something I can do that will make this a little bit more user friendly. Let me just go ahead and stick this up in the numerator so it's clear where it actually exists. That might make it a little bit easier as opposed to bringing it kind of midway down. Now let's just invert and multiply. So of course the even powers go downstairs too. That'll be easy to work out algebraically. So to the 2n, 2 times n, last factor, and then of course we have x to the 2n plus 1, the power of x. And then upstairs we just get the odd factors, 3, 5, 7 to 2n plus 1. close. Now, we don't have to rewrite all of this. It's clear that we can do the absorption process without having to write all these factors again. Sometimes we make that choice just so we can move through the problem a little bit more quickly. So now we can go ahead and box the factors that will clearly absorb. So I'm going to put this in red. Notice I never put slash lines. Boxes are fine. I don't want to see slash lines ever again. That is the worst habit that math students have. Well, it's probably one of the worst. I just don't want to see it. It is ridiculously horrible notation. And I don't know why it's taught. I never did it. I never did it. I guess maybe the math gods were, Professor Ron, I don't want you to do this. So I didn't do it. So now here, just box it. These go away. These absorb. So we're thinking, we'll just go ahead and write the x's down just to make sure we've got that down. So what does this leave us with? The limit as n passes to infinity. And so notice we have the 2n plus 2 and the 2n plus 3. They survive in terms of the factors that contain the n's. And then, of course, here we can use the laws of exponents and write this as x to the 2n plus 1 times x squared. Just use laws of exponents and x to the 2n plus 1, just to make that a little bit easier to read. So now you can see that clearly all of these powers of x absorb, but we're left with the x squared, okay? So this is what I was talking about. Sometimes it's better just to go ahead and apply the ratio test just to make sure you don't leave out any steps. So now this gives us what? 2n plus 2 divided by 2n plus 3. And then, of course, the only thing that's left here is the x squared. But you're thinking that's the absolute value. That's just the absolute value of x quantity squared. So you can just write x squared, or you can write the absolute value of x quantity squared, whatever. They're equal. But I don't want you to think I'm just ignoring the absolute value. The arithmetic is obviously still the same. So now the x squared has no n dependence, so it can be factored. So again, very straightforward, very rudimentary, but important steps. Every step is important. Unfortunately, every step is important, as we know in Calculus 1 and Calculus 2. So now, of course, the ratio of leading coefficients, this is just 1, so this limit's 1, and we just get x squared, or the absolute value of x squared if you just want to keep the absolute value hanging around. So now for convergence, and this is important, we have the absolute value of x quantity squared. Of course, we had coefficients here. That would make it even more complicated, but we don't. It's just a 1. So we have less than 1. So now we can apply the square root function. It's an increasing function. So this is the absolute value of x less than 1. So these are equivalent. And then, of course, the conjunction just says that x lives between -1 and 1. So that's what we have, at least from the ratio test. Again, remember, ladies and gentlemen, when you apply the increasing function to this inequality, that again is increasing, so to speak, it's preserved, just like with integration. So that's something you've used often, and we do it often without thinking about it, but it's often, I'll use the word often too much. It's a good thing to remember it. Okay, so now you're looking at this, and this is where I thought we're gonna have to work a little bit harder. We need to check the endpoints. So one thing I noticed here for this particular example is that we actually need a lemma. And I just created a lemma for this problem because without it, you're gonna struggle a little bit trying to figure out what's going on here. Because when you start looking, if you replace x with 1 and you look at this and you think about this in the situation that we have here, you're like, okay, I get 2/3, 4/5, 2n over n, 2n plus 1, and you're like, what do I do with all those factors? I mean, how do I do this? I mean, we don't have a test that resembles that. So here's what I came up with, because you look at something and then you say, I think I'm going to move this way, but I have to set this up in a way that makes sense. So here's my lemma. This is where the good old induction from pre-cal comes into play. So it's going to look like this. For n greater than or equal to 1, we have 3/2 times 5/4. So this appeals to your intuition, 7/6. So basically what I'm doing is inverting this, because you're thinking I'm going to apply the direct comparison test. And then we have 2n plus 1 divided by 2n. This is less than or equal to 2n plus 1. So the key here is we're looking at all of these factors here. They're all less than 2. They're bigger than 1, but less than 2. Okay? And so as you keep marching along, you're thinking, you know, can I say this? Well, this is easily proven by induction. So I can say you can prove, and you should do this, prove by induction. The proof is very simple. Again, you check n equal 1, which is clearly true. 3/2 is certainly less than 3. And then you can do your induction hypothesis and knock it out in no time. So this is actually valid. So now with this lemma, we have the details that we need. This is what I was talking about before, when students just say, oh, well, you know, it's clear. No, it's not clear. You need this argument to push these forward. So let's check x equal 1. So check x equals 1. It's not sufficient to just say it looks like this is what's going on. Looks like means that the plant may blow up. Okay, you can't build a bridge, you can't make deductions. Well, I think it looks like this. If you're a STEM professional, you must support any decision you make. Oh, it looks like this. I mean, I have to really emphasize the fact that when you're working with mathematics, you can find a solution, or you can find something that'll say, don't do this right now, because you don't have a solution. All right, so that would be the better decision to be made. So now when we go up here, we've got what? N equals 1 to infinity. Then we have 2, 4, 6, 2n, and then 3, 5, 7, 2n plus 1. And then, of course, if we replace x with 1, we just get 1 to the 2n plus 1. Well, that's just 1. And of course, we don't have to worry about a 0 in this case, so we're off the hook. So this gives us this series, n equals 1 to infinity, 2, 4, 6 to 2n, and then 3, 5, 7 to 2n plus 1. Now, when you look at this, you're thinking, okay, we can do a comparison. So when we use this lemma here, this takes us right to this. So by lemma, now, of course, I come up with this lemma based upon the fact of thinking where I need to go, because I think this is going to diverge, because I'm thinking of 1 over 2n plus 1. So now by lemma, we have 3/2 times 5/4 times 7/6 to 2n plus 1 divided by 2n is less than or equal to 2n plus 1. And this is n greater than or equal to 1. Okay, now we're going to reciprocate. So now we get 1 over 2n plus 1 is less than or equal to, of course, when we reciprocate this, we get exactly the nth term of the series. So now you see why I did this. And so my reasoning was that this is what I need to have some kind of handle on. and then you easily prove it by induction and you're good to go. You've got the ingredients you need. So this is less than or equal to 2 times 4 times 6 to 2, the factor 2n, and then 3 times 5 times 7 to the factor 2n plus 1. Now, of course, this is positive. So now we observe the following. This series, n equals 1 to infinity, 1 over 2n plus 1, and we've done this a million times, diverges by integral test. And that's an easy proof. We've done problems like this many times. And so the key here is that we're making a comparison. And the comparison is what allows us to make a conclusion about this. Now, of course, this positive term series, this nth term, creates a divergent real series by the integral test, and therefore by the comparison test, this series must also diverge. So this implies the series n equals 1 to infinity, 2, 4, 6 to 2n divided by 3, 5 times 7 to 2n plus 1 diverges by direct comparison test. So we don't exclude x equals 1. So again, you look at this and say, this is where, when you've got these finite products, the ratio test knocks everything out. That's like easy peasy. I mean, just nothing to do. Very simple. But when you're checking the endpoints, you don't have the luxury of being able to work with something that's going to give you something you need. If you try to apply the ratio test or the ratio test to this, you just get 1, okay? And 1's inconclusive. So that's where you're thinking, oh, well, why didn't we apply the ratio test? Well, go ahead. The 2's there are going to just beat you up, just like they did here. You're always going to get 1, and 1 is inconclusive. So there are limits to the ratio test when it comes to a series like this. And now you're thinking, what about -1? Well, that's even easier because we already done the work and we don't have to do it again. Let me show you how that is simple. So with all this work, we're pretty much done. So we say, what about x equals -1? When we check that, if we substitute, let's just write it down. We're just going to get the negative of the previous series. So we're done. So we don't have to do any more work. So we get factor 2n, and then we have 3, 5, 7, 2n plus 1. And then, of course, we have -1 to the 2n, and I'm just going to write this, the plus 1, as a -1 here to the 1 using laws of exponents. So now what we see is that the 2 here just gives us the +1. So we just get the negative of the real series that we generated before. So this just gives us the negative of n equals 1, 2, 4, 6. That's why it's important to write everything out. And again, this is good practice. It's important to be able to analyze in a way. It's kind of like doing pre-cal. It's amazing when I teach pre-cal, the students resist writing any math out, and then they finally realize if they want to pass my test, then they have to start writing some mathematics. And so what's important here is that it's kind of like we're in pre-cal. It's like, all right, so let's apply, now we've done the pre-cal part, the laws of exponents, now let's apply the calculus. Well, this is the previous case right here. This diverges using x equal 1 case. So we're done. So I don't care if you take the negative of it, it's still divergent. Negative infinity is just as bad as infinity. So this implies exclude x equals -1. I'm not impressed by busy work, okay? I never do busy work. I do the work that you need to do. Doing extra work just because you think it's good is never the case. As a professional, you want to make sure that you're doing tedious work when it's required, but you always want to do good work and check what you do. But busy work's not going to get you to the finish line. Doing the correct work gets you to the finish line. So now this implies interval of convergence, is, again, we didn't get any new looking at the endpoints. So this is why it's important at times to think about, if you think about this in this particular case. Where did I write that? Oh, it's right here. When you think about what we did here, as you start to look at something and say, I bet that diverges, you have to come up with a little lemma that's going to give you the ingredients you need. And if it means that you do a little sidebar calculation with induction, then that's fine. That's part of doing mathematics. We think about what we expect, as we utilize other businesses and things and all. We expect good service. Well, as a STEM professional, your clients are going to expect good service. And so again, if you have to do a little side calculation, even better. Now, what I said before, which is actually kind of important, is that since we're in a calculus class, you're thinking, we're doing limits, Professor Ron. Where are the derivatives? Where are the derivatives and the integrals? Well, when it comes to power series, we remind ourselves that if there's a way to execute calculus, it would have to be done the way we actually differentiate and integrate a polynomial. So even in the infinite case, when we define differentiation, we do it term by term. When we define indefinite integration, we do it term by term. So this is extremely important. And again, one of the major results in calculus that allows us to move this theory forward. Otherwise, we'd kind of be stymied and thinking, well, what happened to differential equations? What happened to partial differential equations? What about all these infinite series? So now, not only do we have the techniques of power series, but we have Fourier series. And that's even a more huge result in real analysis and even complex analysis. So for instance, to introduce the calculus, we refer to the calculus of polynomials. So we just make an extension. We love the power rule. We live for the power rule. So again, the first one is term by term by term differentiation. And the reason, you can just call it differentiation, but it's going to be term by term differentiation. So if we think of f of x equals, just using our favorite letter for a function f, we have n equals 0 to infinity, a sub n. I'll just go ahead and write the more general series that's centered at c. Okay, again, a lot of the ones that end up in the charts are going to be Maclaurin-esque in that the c will be 0. But for now, let's just go ahead and keep it in a nice general setup. So the idea here is that we can think of this as a sub 0 plus a sub 1, x minus c to the 1, plus a sub 2, x minus c squared, etc. So term by term, so this if and only if f prime. So we can think about this, we can think about differentiating the nth term and see what we get, and then maybe adjust the series index-wise, maybe because we have some zero terms. So for instance, power rule, we bring the n down, so we have n times a sub n, x minus c to the n minus 1. Okay, of course, if we look over here, this is of course 0, and then we just get a sub 1, and of course, x minus c, 1 minus 1, that just leaves us the a sub 1. Then we get plus 2 a sub 2, x minus c to the first power. And then for the next one, we get plus, so we bring the 3 down. I'll just imagine I put another term right there, 3, a sub 3, x minus c squared, etc. So if we're going to be able to include the calculus with the power series, we have to define the differentiation process term by term. And this turns out to be very consistent with the theory that we've already developed. Because if we fix an n, then we have a polynomial. How do we differentiate a polynomial? What? Power rule. Okay, so this is consistent with the calculus that we've already developed. So that's why I write term by term. Now, of course, look here. If I have n equals 0, then of course the first term is just 0. We've got 0, a sub 0. So I don't really need a 0 term. So I could just say equivalently, and of course this will change. We can say f prime is just the series where we start at 1, if you like. So we'll say n a sub n x minus c to the n minus 1. Of course, we can re-index and do whatever you like, but notice here the 0 term just gives us 0, so we can just start our series at 1. And this tends to be a typical way to write it. But you are free to start wherever, re-index, that you are completely flexible in that area. It's like when you're doing your integration process, you are in charge. So how you write something is completely up to you. And maybe you write it a particular way so that it's easier to work with. Okay, so this is what I'm talking about. As long, like when we work with geometric series, we would re-index so we could add them. If we want to add series, then we have to make sure that the powers of the power function are actually consistent. So it's like adding x squared plus 3x squared. That's 4x squared. But we can't add, x to the n and x to the 2n. Okay, those are different terms. So we have to re-index if we can. Maybe we can't, but we can always try to re-index to make sure that we can combine things in an algebraically legitimate way. Okay, just like you've always done in algebra. So when we think about term by term differentiation, we get a formula like this. Now, I don't want to say that you should just apply a formula to everything. It's probably better just to go ahead and apply the power rule. And then if you got a 0 term, get rid of it, okay? And then you don't have to, memorize anything. But this kind of gives you a general way of thinking about differentiating a power series. Just think of like what we've done here, differentiating term by term, and then collapsing it to the general term like we have here, okay? Now, integration is the same way. Term by term integration. But we have to work a little bit harder with this, but not much. We're going to think about having an interval of convergence too. So term by term integration. Because if we fix an n, what do we have? We've got a polynomial. And what do? We add 1, divide by the new power. Okay, so we don't have to invent any new calculus to do this. So now what we want to do is we're going to assume, say we have an interval of convergence. Interval of convergence. Now, if we have a radius of convergence, what we can do is we'll fix x naught, x sub 0 to live here. Say c minus r to c plus r, okay? Just to live in the interval of convergence, a fixed. So when we do an indefinite integral, our first limit will be fixed, okay? So we know something about that. We know the series converges for this particular real number in the interval of convergence. So now when we think about this, we'll say, okay, well, we have f of x equals, we'll do the same thing we did up here, ladies and gentlemen, just use the x minus c just to make it more general. N equals 0, a sub n, x minus c. And so we're going to do indefinite integration. So execute indefinite integration. So we'll say the integral from x sub 0 to x, and I'll just use a t here since I've got a bunch of x's running around. That gets too unclear if I don't change up the variable like we're doing the fundamental theorem of calculus. So we'll do term by term. So we'll switch the integral in the series. So this is n equals 0 to infinity. Then we have x sub 0 to x, a sub n, t minus c to the n dt. So this is only to make it clear that since we've got x's in the limits, we just change the variable here to t, just because too many x's, it doesn't really make any sense. So now what we do, this is a power rule, add 1, divide by the new power. So this will be the series n, and then we'll apply the fundamental theorem to our indefinite process here. So we get what? A sub n divided by n plus 1. And then we have t minus c to the n plus 1 evaluated x naught x. Okay, so we're looking for a general formula. So when you think about an indefinite integral, this is basically what you do in calculus, but we're tying in the interval of convergence to make the evaluation of the constant seem to be more legitimate. So now we'll just replace t with x. So this gives us what we expect, n equals 0 to infinity, a sub n divided by n plus 1. And then, of course, this will be x minus c to the n plus 1. And then what do we have here? We have the x sub 0. So this equals, n equals 0 to infinity, a sub n, n plus 1. And then we get x sub 0 minus c, n plus 1. Now, one thing that we have to use here that's very important for term by term differentiation, r is unchanged. You can apply the ratio test to prove that. The radius of convergence is unchanged. For term by term integration, r is unchanged. So you're thinking, if we apply the integral here or the derivative, we have the same radius of convergence as the original series f here. So the integral of f has the same r. The derivative of f has the same r. You can apply the ratio test. It's very simple to apply that. And you can apply arguments that are much more finessed or whatever, but the key here, and this is really what makes, again, this work, not only do we execute term by term differentiation and integration, we also utilize the fact that the radius of convergence does not change with these operations. However, you still need to check endpoints. We never get the endpoints for free. So as you move from the series to the differentiated series or the series to the integrated series, you must check the endpoints. And like I say, that's an easy verification with the ratio test. Now, what we can see here is that this, again, is a convergent series because we have taken, and of course, when I wrote this, you knew that this had to be the case because I wrote this. The idea is that this is a convergent real series. So this is a convergent real series by hypothesis. So as we move to the next page, what we can say is that this negative real number, we take the additive inverse of this, we subtract it, we're going to just call that the plus C. So that's going to give us the constant of integration for our indefinite integration. So this will be this number here, we'll just call C. We'll just go ahead and couch in the minus sign there and call this C. So what does this give us? Well, it gives us lots of power. So if and only if the integral of the series f of t dt is now the series n equals 0 to infinity, a sub n divided by n plus 1, x minus c to the n plus 1 plus a constant. And of course, where f of x is just the original series, n equals 0, the power series, a sub n, x minus c to the n. So this is exactly what you expected. If you just kind of remove all the other stuff and you don't put any limits on the integral, you can kind of just say, oh, well, it's add 1 divided by the new power plus a constant. But sometimes students get fairly sloppy when it comes to evaluating constants. And we need to be a little bit more particular because, again, when you start to do an integration of a series, you want to sometimes make a convenient choice of some real number in the radius of convergence to make the calculation of the constant much easier, okay? So this is an important construct that just gets swept under the rug for some reason. I don't know why. And you don't need to guess about anything. So let's look at an example of this. So let's apply this. So for the next series, what we want to do is we want to integrate it and differentiate it. But since we know that R does not change, we'll look at the original series to figure out what R is. So in this case, we have an example. So we'll say, well, let me call it F. We're not saying that it converges to a particular function yet, but we will designate it as F. So this will be n equals 0 to infinity, negative 1 to the n plus 1, x minus 1 to the n plus 1, divided by n plus 1. Lots of n plus 1s. So basically what we're going to do is compute intervals of convergence for, in this case, we'll do f prime and the integral. Now, when you look at these and you think about what we need to do, the fact that we know where things are centered is going to make things a lot easier for us. We'll just have to check endpoints. So that the process going to the derivative and the integral is not always a tedious one. So we just need to analyze f first. So now let's do the ratio test. N passes to infinity. So we have negative 1 to the n plus 2, replace n with n plus 1, x minus 1 to the n plus 2, replace n with n plus 1, n plus 2, then flip everything. So we have x minus 1 to the n plus 1. And then we've got the, well, let me put that on the other side since there's really not enough room there. It'd be hard to squeeze that in. So we'll say times negative 1 to the n plus 1. And then upstairs, we just have n plus 1. Okay, so now let's go ahead and do the algebra. So n passes to infinity. So we've got the, in this case, if we think about it, we've got the negative 1, and we have the negative 1 to the n plus 1. Just go ahead and put the negatives together. Negative 1 to the n plus 1. So those will absorb, leaving us a negative 1. And then, of course, we have an n plus 1 over an n plus 2. So just go ahead and just check those off. And then, of course, now we have x minus 1 to the n plus 1 times x minus 1 to the first power using the laws of exponents, and then x minus 1 to the n plus 1. So again, it's like we move back to algebra 1 to do laws of exponents. So we have the limit as n passes to infinity. So of course, all of these terms absorb. The minus 1s are gone. That's fixed. And then the n plus 1 powers of x minus 1 absorb. So this leaves us with, of course, the absolute value of negative 1 is 1. So this leaves us with n plus 1 over n plus 2, a nice positive quantity. And then, of course, the absolute value of x minus 1. So again, we always probably are better off looking at the ratio test just to be sure that we don't leave anything out. And I found this to be a little bit better at times when students start to get a little bit sloppy. I think that this maybe is worth the little extra time that it takes. So now, of course, the x minus 1 is independent of the n, so it can be factored. So this is x minus 1 in absolute value, the limit as n passes to infinity of n plus 1 over n plus 2. Well, of course, ratio of leading coefficients, we get 1 here. So we just get 1 times absolute value of x minus 1, which is absolute value of x minus 1. So for convergence, we have the absolute value of x minus 1 must be less than 1. So equivalently, a nice conjunction, an easy one, albeit, negative 1 less than x minus 1 less than 1. And of course, we'll just add 1. 1 plus negative 1 is 0. And then, of course, 1 plus 1 is 2. So at least for now, we see in this particular case that we have this open interval 0 to 2. And so we need to check the endpoint. So now at least, let's just go ahead and mark this down. We see R equals 1, okay? R equals 1. So for the differentiated series and the integrated series, we have R equals 1. So we don't have to start from scratch with that. We don't have to go back and do the calculation from scratch. We just need to check endpoints. So remember, as you differentiate and integrate a power series, the R is unchanged. You still, however, must check the endpoints, which we need to do here. So let's do that. This is fun, isn't it? I mean, when you think about it, this is like doing integrals, but interesting. When you think about what we do in calculus, there's always something fun, and you think, well, we're still adding numbers, we're dividing numbers, we're getting common denominators, laws of exponents, still doing the same techniques, but hopefully building a foundation to do some more interesting problems. So first, let's check x equals 0. So let's go to the original series. So we have, in this case, let me just write it. That's f of 0, but let's just write the series for now, since we don't have an actual convergent function. So we have n equals 0 to infinity. So we have negative 1 to the n plus 1. And then we have, in this case, 0 minus 1 to the n plus 1. divided by n plus 1, okay? So again, remember when you check the endpoints, you just simply replace x with the given endpoint. So now, of course, this will be the series n equals 0 to infinity. So we have -1 to the n plus 1 times what? -1 to the n plus 1. So now you just add the powers, we've got the same base. So this will be n equals 0 to infinity. So this gives us -1 to the 2n plus 2. But now, of course, with all these even numbers, -1 to the 2n is 1, and -1 to the 2 is also 1. So we just get the series n equals 0 to infinity of 1 over n plus 1. And so, of course, now this we know by the integral test diverges. You can compare, but this is an easy integral test. So clearly diverges by integral test. Now, when you have something that's fairly straightforward, I'm not going to beat you up and say, oh, okay, you got to check all the hypotheses and stuff. This is a very basic example that we've done, okay? And so I'm going to give you the fact that if you can at least quote a convergence test that gives you your conclusion, then that's fine. If you don't write that, then it's wrong. But I am not going to demand that you do a complete analysis of this. You need to just clearly say, by the integral test, this would give a divergent series, and you could say the improper integral diverges. That is, the improper integral 1 to infinity, 1 over 1 plus x dx is infinity, okay? That would be sufficient. Clearly, this is positive, it's decreasing, you know, that we need in continuous as a real valued function. That I can give you some flexibility. However, if this was the only part of the problem where you just had to look at this series, then you'd have to do the complete analysis, which many of you failed to do on the last test, which again made no sense. But if you've just got the one problem, then you need complete detail. If it's a smaller problem in a bigger example, then I can say, okay, this is a divergent series by the integral test. We will not get convergence at 0. So this implies exclude x equals 0, okay? So you're seeing that all of this is tied together now. Now let's check x equals 2. That was the other endpoint. So we have the series n equals 0 to infinity, -1 n plus 1. And now we've got what? 2 minus 1 to the n plus 1. Well, this is going to give us a lot nicer. So, of course, that's just going to be 1 to the n plus 1. So this is going to give us a nice alternating series. So we get -1 to the n plus 1 over n plus 2. And now, of course, again, we've got the a sub n for this particular case is 1 over n plus 1, which clearly goes to 0, and this is non-increasing. So just kind of a quick little check, just like I did here. And then, of course, this would say, says converges by alternating series test. So you don't have to write a book with these. You now know these tests very well, and you can do a summary here. So this means include x equals 2. So for F, this implies interval of convergence will be 0 to 2. 0 not included, 2 included. Okay, now let's write the original series. So we have f of x equals, so we have, I'll write this again so it's clear, n equals 0. And we have what? -1 to the n plus 1, x minus 1 to the n plus 1 divided by n plus 1. So now let's do the term by term differentiation. So this implies f prime. So we have n equals 0 to infinity. So we have -1, n plus 1. Of course, that's not any x, so that doesn't change. So we have what? N plus 1, x minus 1, and we subtract 1, so that just leaves us with an n. Good old power rule, divided by n plus 1. Again, power rule for differentiation. The n's, the functions of n alone, have no x dependence, so they're just constants. So this gives us the series. Now notice the n plus 1's absorb. So here, absorb. So we get n equals 0 to infinity, -1, n plus 1 times x minus 1 to the n. Now, here's what's interesting about this particular series here. Notice with the n plus 1 here, we just get 1 here. So when we bring down the n plus 1, we just get 1. And so now we don't get a 0 term, so to speak. So when we differentiate this, n equals 0 is actually non-zero. That is, we're going to get -1, and here when n equals 0, we just get a -1 term. So we can't just kick out the 1 here, or the first term, because we notice that we start with an n plus 1 here. And so when we descend here, these do absorb, but the n plus 1 is not 0 when n equals 0. So we get a more interesting formula here. So you can't always jump to the formula. It really depends on what the coefficients of the power function happen to be. So now remember, r equals 1 for this new series. So let's check the endpoints. So we have check x equals 0. So here's our differentiated series right here. So let's put a box around it. This is f prime. And so now when x equals 0, we get the series n equals 0 to infinity, -1, n plus 1. And then, of course, we get 0 minus 1, n. So this gives us the series n equals 0 to infinity. And so let's add all these up. So we get -1 to the n plus 1 and -1 to the n. So by laws of exponents, this gives us n equals 0 to infinity. So we have -1 to the 2n plus 1. Of course, -1 to the 2n just gives us 1. And then, of course, to the 1 just gives us the negative. So this is just what? -1 added to itself infinitely many times, which clearly diverges. So again, +1, and then of course here, -1. So this clearly diverges. Why? Divergence test. -1 never has limit 1. So diverges by divergence test. So we like series like that. There's no work. We don't have to work to do them. I mean, these are the easiest ones. So let's check the other endpoint. So this means exclude x equals 0. So let's check 2. So it's like we're working in an accounting office, right? So now check x equals 2. Again, we're not having to start from scratch because, again, we know r equals 1. So all we have to do is check the endpoints. We already know that gives us 0 to 2. So we'll check 2 in this case. So let's just see what we get. We have n equals 0. Just write down the series that we boxed before. -1 to the n plus 1. And so we've got 2 minus 1 to the n. So that's just 1 to the n, right? 1 to the n, which is just 1. So this gives us an alternating series. So we get -1 to the n plus 1. Clearly here, a sub n, well, we don't even have to do that. We're done. This sequence is -1, 1, -1, 1, -1, 1. So we'll just say the limit takes a little more work. N goes to infinity of -1 to the n plus 1 is clearly not 0. It doesn't even exist. So diverges by divergence test. So we exclude x equals 2. So the thing here is that we know if the nth term does not have limit 0, we get automatic divergence. I mean, it has no limit. It's either 1, -1, 1. Subsequently, it has a limit, but as a bona fide sequence, there is no limit. So again, the interval of convergence, interval of convergence, and I'll just say for f prime, doesn't include the endpoint 0 to 2. So I think when it comes to working with series, at least with the differentiated part and integrated part, we don't have to start from scratch. Now let's look at the original series and finish this off. So we have in this particular case, n equals 0. Here, let me write down the original series. I don't want to jump to the integral. So this will be -1 to the n plus 1, x minus 1 to the n plus 1 divided by n plus 1. So in this case, r equals 1, as we know. And what we want to do in this case, again, is fix. So we're going to be real lazy. This will be good. Fix 1, which lives between 0 and 2. Okay, so we're going to do 1 because 1's going to annihilate this. So now the integral 1 to x of f of t dt will equal the integral. So now we can interchange limit and integral. So we have n equals 0. So now we've got the integral 1 to x, -1 n plus 1, t minus 1 n plus 1 divided by n plus 1 dt. So now add 1, divide by the new power. So this will give us the series n equals 0 to infinity, -1 n plus 1 t minus 1 to the n plus 2, add 1, divide by the new power. So that gives us n plus 2 times n plus 1, evaluated from 1 to x. So of course, this will give us the series we thought we would get, n equals 0 to infinity, -1 n plus 1. So of course, that'll give us x minus 1 to the n plus 2. So that gives us n plus 2 times n plus 1. This is certainly a lot easier than applying the ratio test. And now if we put in 1, that's going to kill off everything. So minus n equals 0 to infinity, -1 to the n plus 1, 1 minus 1 to the n plus 2, n plus 2 times n plus 1. Now, of course, here, when n equals 0, we don't get anything indeterminate. This is just 0 to the 2. So all of these terms go to 0. So this is completely 0 for all n. So we just get, so basically what we see here is that the constant of integration is 0 if we're clever to choose a value here that helps us to see that. Otherwise, you're struggling. So here we see this implies the constant of integration is 0. So we're just left with n equals 0 to infinity, this object right here. negative 1, n plus 1, x minus 1 to the n plus 2, n plus 2, n plus 1. Okay, now, of course, the r is 1, so we just check the endpoint. So let's check x equals 0. These are quick. So we have x equals 0. We get n equals 0 to infinity, negative 1, n plus 1. Now, of course, we get negative 1 to the n plus 2, negative 1, n plus 2. And that extra factor downstairs is good, isn't it? So now we get n equals 0 to infinity. So, of course, now we get the 2n plus the 3. So this will give us negative 1, 2n plus 3. So, of course, here the negative 1 will just survive, just a minus 1. The negative 1 to the 2n is clearly just 1. So this is n plus 2 times n plus 1. So we just get the negative of this series, n equals 0 to infinity, 1 over n plus 2 times n plus 1. Now, when you look at this, we're thinking, okay, this will be an easy direct comparison test that we've got the negative, that doesn't matter, but we can say converges by direct comparison test using the p-series, right? N equals 0 to infinity, 1 over n squared. You can use that and just take the reciprocal because, of course, the n plus 2 times the n plus 1 is going to be greater than this guy here. Or you can just use limit comparison test, either way you want to do it. So this means include x equals 0. So that's a check there. So do a little extra work there to finish that argument off. That's something we've done many times. And then x equals 2, we'll have, let's go ahead and fill in x equals 2. So again, notice here, our series right here. So we'll fill in x equals 2. So this will be n equals 0 to infinity, negative 1 to the n plus 1, 2 minus 1 to the n plus 2, divided by n plus 2 times n plus 1. And now notice that this is just a 1, so this is 1 to the n plus 2, which is always 1. So this gives us an alternating series. So n equals 0 to infinity, negative 1, n plus 1, n plus 2, n plus 1. And now, of course, a sub n is 1 over n plus 2 times n plus 1, which clearly goes to 0, and a sub n is non-increasing, clearly. So we'll say converges by alternating series test. So this means include x equals 2. So what we're seeing is that with power series, we've got to quickly infuse the real series test at the endpoints. Away from the endpoints, the ratio test takes over. But the endpoints can usually be fairly straightforward. But as we saw in one case, we had to do a little induction lemma to move the problem forward. So now this implies interval of convergence for the integral, in this case, 1 to x of f of t dt is 0 to 2. So we include both of the endpoints. So what's important with these problems, again, is first realizing the fact that the radius of convergence between the differentiated series and the integrated series does not change. So you don't have to do that computation. You look at the original series, compute that, get your interval, and then as you integrate and differentiate, you'll just need to check endpoints. You won't have to worry about doing the process over because the interval is not going to change. The that is the radius of convergence is not going to change. The only thing you have to do is look at the endpoints like we did with the differentiated series and clearly the integrated series. So hopefully you found this to be at least somewhat edifying, because not only do we keep reviewing what we've done with the real series, is that now we can see the huge utility of the ratio test to give us that nice symmetric interval about C. So power series are really, really very well behaved, ladies and gentlemen. They are good objects. They make sense arithmetically. So what are we going to do with this for the next lecture? We're going to now try to push in the f of x. It's like, can we rig these examples so that we actually know the function of convergence? That is, if we have this power series, can we say, oh, this actually converges to this function? Because that's going to be even a higher level of thinking that we haven't seen with the problems that we've been doing. So that's what we're going to do at the next lecture. Again, a little bit long-winded with this material, but we will continue the saga with our next lecture. I'll send out email invitations for conference hours. Thanks for your attendance today. Again, I hope you find this interesting. This is such critical material. This is fundamental. And every time I say fundamental, you think, Professor Ron, you say everything's fundamental. Well, ladies and gentlemen, when it comes to calculus, it is, because it touches every aspect of real and complex analysis. Okay, well, like I say, I'll send out the invitations. You all have a great day. Good luck with your studies, and we'll see you later. Bye.